problem where we finished it up kind of quickly, where Super Spider-Man drops his wallet, right? And it goes to the bottom and falls a height of 85 meters, right? And so when we filled that stuff in, we realized that our delta S was negative 85, right? Because it's going down. That we started, since it was dropped, with a 0 meters per second initial velocity. And that acceleration downward is at minus 10 meters per second for each second. Okay? And, yes. Well, it's a rate of a rate, really, because velocity is a rate in itself, because that's the rate of change of your distance moved for time, right? Or displacement for time. So that's how many meters per second. That's velocity. But then acceleration is change in velocity with time, right? So that's meters per second over seconds. A meter per second. So that's why you have the velocity change. That's meters per second, but it's the velocity change over time. So if you increase your speed by 10 miles per hour every minute, then your acceleration is 10 miles per hour per minute. Right? You see? So in this case, we just have seconds twice, so it becomes seconds squared. All right. Classic, right? Really. So if we do our Wolf squared equation, one person laughed, that's good, equals V squared plus 2A delta S. And so VI is 0, so that drops off. Now this is an equation you would want on your sheet, right? Because you could put these equations on your sheet, only the equations, right? Smiley face, I rip it up, right? So be careful if you doodle. No, that's not true. You just can't put information that's helpful. Like, you know, you can put the equation, that's helpful, but you can't put other helpful stuff that should be up here. So this gives you 17, then we square root it, we get minus 41. So it's going past 40 meters per second as it goes. Now, we could fill in the rest of the chart. Our average velocity there would be 20.6 minus, right? We'll make it blue. Delta V. Now, I did that by this plus this divided by 2. And then delta V is VF minus VI, which would just be minus 41.2 meters per second. How am I going to get delta T? How am I going to get delta T? You could sit here. How am I going to get delta T? Change in V over A. Okay, so since A is delta V over delta T is delta V over A. It's kind of nice with the gravity ones, acceleration due to gravity of 10, because you have minus 41.2 divided by minus 10 meters per second squared, and that just gives you 4.12 seconds. Okay? You just move the decimal place over 1. So we've looked at some 2 3s, 2 2s, and 2 1s. Now let's go and look at some 2 4s. But we're not really adding much here to it either. Just the fact of that you can get to what the acceleration is in the plane. Yes. Yeah, sometimes. Well, see, if it's if you have like if you end a velocity here, it might be your initial velocity there. So stuff like that you can do. That was the raccoon one. So you had a reaction time. Is that where you hit the? No, that's where it fell, right? It crushed the raccoon. Yeah. So when she fell, she picked up speed, right? Now she reached the final speed in this. That becomes your initial speed when it hits the raccoon, smooshes it. When she smooshes it, it goes from a high speed to 0. Then you could figure out the acceleration and stuff. It would probably be pretty high. Yes. I don't think the raccoon did well. But luckily she was okay. No, I don't want you jumping. But we're going to have chances to do some more problems. So anyways, let's see the novice skier on page 5. Did you see, I showed you in one of the videos how to calculate how it comes the angle of the incline, and that the acceleration down the incline is sine 10 times sine theta, right? Because of similar triangles. Now you might not have started similar triangles in geometry yet, but when you do, you'll see like you have those similar angles there. Actually, yeah. So the novice skier goes down an incline, the bunny hill, and it's at 12 degrees. Okay? We could probably find a skier here. Is it IER? Come on. I don't know why that didn't work. Is it II? Uh-oh. It's not working. You see, you have to snap to get it to go into place. Let me try something again. I don't know why that doesn't work anymore. No, it's not that. It's Tommy, be quiet. All right, there he goes. Oh, we got it. Sorry. Entertainment value. Now, with that, we have a double chart for that one. We're just going to go to this one. I don't know why. Why does it have a double? Did it need one? Anyone do this problem? I guess it does. He goes down the hill after traveling a distance of 50 meters. Oh, she smacks into a stack of hay bales. Huh? It's so because they can't stop. They don't know how to stop. Yes, that is why. Which stopped her motion, fully analyzed both her descent and the crash. So she starts. She starts up here. VI is 0 meters per second, and then it says 50 meters. She's going down 50 meters, so we'll put negative 50 meters here. We have our hay over here. That's hay stacks. And then, so that's all that's given for the first part. But, and 12 degrees. What can we do with that 12 degrees? We could find acceleration from it because we know that A parallel, that's what that means, parallel, is G sine theta minus 10 meters per second squared times the sine of 12 degrees. So we just asked Celsius what that is. What is minus 10 times sine of 12 minus 2.08 meters per second squared? G is the acceleration due to gravity, minus 10. That's just the first one. We're going to do the first one first, and then the hay bales next. Okay, so she'll crash into that. Yes. Wait, say the acceleration what? Oh, well, parallel just means parallel to the slope. Yeah. So, okay. What are we going to find here? What should we find? With what? Can we say correctly, please? Boof squared. Right? The final velocity squared, that's 0. 2 times minus, 2.08 meters per second squared times minus 50 meters. Calculate it. 208 meters squared over second squared. Now what do I do? Square root it, right? $14.4. Now is it plus or negative? Negative. Good. Because we're going down, right? Sometimes it's set up, well, It depends how you define your plus y and negative y. So, but in this case, I think it's just easier to keep it negative to be consistent with the other way. Yeah. Well, you could call down positive. Then this would have to be positive, that would be positive, and that would be positive. Huh? You could do that. Alright, so average velocity, 14.4, well, I should write it down. It's always good practice to write the formula down. So if you make a mistake, even if it's a stupid mistake, by like leaving off a number in your calculator or something, then if you have the formula written down, I can see, like if you wrote this formula and you have 6.1 written down, I know the formula's right, you know what I mean? So I can give you some points. Oh, and it's negative. Okay, so I've switched pens so much that the colors really make no sense. So now delta V is VF minus VI, which is negative 14.4. How are we going to get delta T? Well, okay, now you were saying the delta S one, because you could use V bar as delta S over delta T here too. So we could use this, or we could also use, nope, it's the opposite way. So delta V is 14.4 divided by 2.08, 6.92 seconds. If we did it this way, we'd have delta S, which is 50, divided by average velocity 7.2, which is the same thing. Neglecting a little bit around, 6.9. Oh, just A, sorry. Question. Now, the little old lady, she hits the hay barrel. What speed is she hitting the hay barrel? What speed is she going to come to a stop? So, do we know anything else about the hay barrel? 0.09 seconds. Okay. So, I have formulas written down that allow me to calculate average velocity. Oh, it's the same. How interesting. Isn't it? But delta V would be VF minus a minus, so that would be actually a plus, wouldn't it? Let me show that. So delta V is VF minus VI, where VF is 0 minus a minus 14.4. That gives us a plus 14.4 meters per second. That would make sense if we were at minus 14.4 and we go to 0, the change is plus 14.4. A, how are we going to get A? We could put it right in, right? Delta V, 14.4. Delta T, 0.09. 160. Ouch. That's like 16 G's of acceleration. Gee. I'm sure it is every day. I was skiing, looking out the window. Oh, yeah, that's a true story. Oh, okay. He said, don't they cross off? Meters per second divided by seconds, right? See that? Because this means divided by. It's the same as meters per second times 1 over second, which is meters per second, or meters per second squared. Yes, Michael. Oh, it's slowing down, but in what direction, though? You see, it's slowing it down in the negative direction. That's why it's a positive acceleration. That gets tricky because both, when you have accelerations, positive or negative, a positive acceleration could mean speeding up in the positive direction or slowing down in the negative. And a negative acceleration could mean speeding up in the negative or slowing down in the positive. Okay? Delta S. Alrighty. V bar was minus 7.2 meters per second, and delta T was 0.09 seconds. So that gives us minus, what? Oh, I did it. 0.648, or 0.65 meters. Negative. Why is that negative? Still going down, not very far, but that's the imprint. 0.64 meters is enough to be imprinted. Okay, so that was 2.4 down a plane. Now when you get to 2.5, you start working with graphs like last night. Absolutely, I will. There you go. We're going to go all the way to page 16. Construct some S and A graphs. I went kind of fast yesterday, video. But the key parts to the video was the slope on a position versus time graph is the slope on a position versus time graph is the velocity. Yes, I did. You can show me after. Don't forget, though. Then you'll have a 0 factored into your grade. You'll fail, and then you'll be wondering, why did I fail? Probably not. The slope on a velocity versus time graph is the acceleration. The area under the acceleration curve, between the curve and the t-axis, or the x-axis, is the what? Well, it would be, no, it would be, no, it would be the change in velocity. See, basically, you have three graphs, position versus time, and we can stack them, velocity versus time, A versus time, okay? Do that. The slope on it, the position versus time graph, the slope on that is the what? Velocity. So we can see that our velocity here is starting out steep, our slope is high, and going smaller. So our velocity is starting out up here and going down, right? And we can see that because what is delta S over delta T? Right, our average velocity. So to get from position versus time graphs, the slope's going to bring us the velocity. Make sense? The slope on a velocity versus time graph is in this case it's negative down here, sorry. And it's constant. The slope's constant, isn't it? And it's negative. See? Because what is delta V over delta T? In chart problems, you get the same results as what you would get when you do stacked graph problems. Now, if I look at the area between the acceleration and the t-axis, area would be a times t, right? Well, that would bring us back to change in v. Because change in v would be a times delta t, wouldn't it? So the area would bring us up here, and our change in v must be bringing us from a higher value to a lower value because it's below the axis. And then the area here, well, that's going to be v times t, and that's going to bring us up to s, or change in s. So we go from a low s to a higher s, but we're slowing down when we get up there. So let me show you a problem where we go from one to the next. Maybe it will come more clear. Alrighty. So, and problem number 2.51, you see that we're going to do on page 16. We have a velocity. We go up 3 units. Oh, but three squares. Each one's 4. You see where it says 4 meters per second for each velocity graph one? So this is 4, 8, 12, and this is velocity meters per second. And then for the time, it's each is 1 second. And we go 1, 2, 3, 4, 11 seconds. Okay? We're just going to do the V right now. I'm going to draw it, and then we're going to work up to S, and we're going to work down to A. Okay? So we start up at 12, and over the next 3 seconds, we go to 4. We'll make that a red zone. And then we stay at 4 for the next 1, 2, 3 seconds. We'll make that the blue zone. Then we drop down to 0 after the next 2 seconds. We'll make that the green zone. It's supposed to go right through that. It just got shifted over a little bit. And then the next 3 seconds, we go down to -8. Okay? We'll make that the purple. So to go up to position here, on our position graph, we'll have the same time. Okay, we'll put that on there. We'll have a different position scale, but I'm not going to calculate it right yet, because I'll wait until I see what it changes. Okay. How do I go from, that's an S, how do I go from velocity to position? What? How do I go from my velocity versus time graph, Courtney? It's the area, right, underneath, between the time axis and the curve. So on this thing, the red zone, this would be my area here. Now, to get that area, it's really, we could do an A1 area up here and then the rectangle one right here, right? So we can do that as A2. So our total A would be A1 plus A2, because it's a triangle sitting on a rectangle, which is also called a what? Trapezoid. But we could you could just break it up and find the area of the triangle and then the area of the rectangle. What? Yeah, that's fine. I end at 11. See? I just put it out to 12. Okay, so my first area here would be 1/2 for the triangle. The base is 3 seconds. And the height of the triangle is 8 meters per second. See that? 3 seconds, base, a height of 4 to 12, which is 8 meters per second. We also have the rectangle down below, so we'll have to add that in. And that would be a base of 3 seconds and a height of 4 meters per second, which would give us 4 times 3 is 12 meters, the seconds cancel, plus seconds cancel again, 12 meters again, or 24 meters. So the red zone gives us a displacement as a result of that average velocity of 24 meters over that time. The blue zone, we'll calculate now. It's only one kind of area. It's just a rectangle. and the area of the rectangle would be just base times height, which would be 1, 2, 3 seconds with a height of 4 meters per second, which would be 12 meters. The green zone would be a triangle, 1/2 base times height, 1/2 the base, which is 2 seconds, times a height of 4 meters per second, which would just give us 4 meters. Everybody following what I'm doing? Right, just calculating areas. And then the purple zone is that, and that's an area is 1/2 the base, which is 3 seconds, but the height here is negative 8 meters per second, which gives us minus 12 meters. Now it says that you start at an SI equal to 0. Your original position, your SI is 0. And from that, with the SI being 0, we could see that how much are we going to go up? We're going to go up 24, then 12 more, then 4 more, and then we're going to drop 12. So 24 plus 12 is 36, plus 4 is 40. So I got to go up to at least 40 here. So I have to go up at least 40 meters. 10, 20, 30, 40. That's fine. So in the first one, I start at 0. The red one, I start at 0. And by the time I get to the end of the red, I've gone up 24 meters. So by 3 seconds, I go up 24 meters. It's right there. But let's see what our velocity does. The velocity in the beginning is higher, right? It's 12. The velocity at the end of that time is only 4. So we start with a higher velocity, which would be a higher slope, right? And a lower velocity, which would be a lower slope, don't we? See that? So the first one is 12. The second one is 4. And if you connect those, you have that curve shape to it. Well, my velocity decreased over this displacement, but it was always positive. It was always above. And that allowed for a positive change in displacement. The initial one was up at 12 meters per second and then down to 4. Okay? Then we keep to 12 meters more, so we're going to go 24 to 12 up to 36. So in the next 3 seconds, we go up to 36. Now during that time, how did the velocity change? It didn't, did it? So it will be a straight line from here to here, like that. And then we get another positive in the next 2 seconds up 4 meters. We'll go up to 0. Up to 40. So let's see what our velocity does. Our velocity starts out at 4 and goes to what? What's our velocity right here? 0. So our slope must be 0. So a slope of 0 looks like that, flat. Over here it's like that. It's got a slight, over here it has a slight positive of 4. But it goes down to 0 over that time. So it looks like this. We've gone up, stayed like that, and then curved down. Then we drop 12 meters, so we go from 40 back down to 28 in the purple zone by 11 seconds. But we start at 0, and we go to a -8. So we have to be like this, -8 by then. The slope's like -8, and it looks like that. So that's getting to displacement, going to the position graph from the velocity. We take areas, right? Okay, so now everybody stand up for a minute. We're going to do the stretch for a second. Good to stretch. I didn't realize this would task. How do you know if it's curved? Okay? The way we found the area, which was the change of 24 meters, right? So we know we went from 0 to 24. Does that make sense? Okay. But we know it's not a straight line because it would have to be flat to be a straight line. So up here, we can look, we know the slope on a position versus time graph is the velocity, right? So my slope, my velocity right here is 12. So my slope has to be about 12. It doesn't have to be exact, but I can see that my velocity here is only 4, so I have a less of a slope and positive. So I go from that to that. And so then I just connect them. Well, I'm eyeballing it. I'm not being exact with it. It's about 5. Yeah, it looks like, I just eyeball. You don't have to calculate. You could do that. Have your curves more exact, but you don't have. We're not going to do that. Just the fact that it goes from a higher to a lower, right? Now through this, what happens to your velocity? So that's why we have the straight line here, because the slope is always the same. Then we go from a high to 0. So then we go from high to 0, right? Then we go from 0 to negative something. So we go from 0 to negative. See? Yes. Well, that's impossible to be exactly straight, because that would mean your velocity, you're changing position without changing time. And for Newton's mechanics, for that to take place, you have to have a time to change the position. It turns out, though, time is relative. So, to the observer and the speed you're moving at. If you have a let's see if I can do this. If you have a double-sided mirror that's shaped at like 90 degrees to each other, and you're on a train and you're moving on the train, okay? And I'm trying to think how this works. And there's a bolt of lightning. I'll have to think about it. For the bolt of lightning to get, if you're traveling on the train, there's a lightning bolt, right? For the person that's on the train, if there's a person standing there off to the side, the lightning hits and it travels to that person, right? Right? So it's instantaneous, almost, but there's a time delay for the light to travel to the person. But the person who's on the train, as they're traveling, that light the lightning bolt hits, and it travels to them, but because they're traveling, there's a slight difference in time. So because the person is they're traveling on the train, that person is going to see the lightning bolt before the person on the ground. So there's, even though it's an event that's happened, one perceives it at one instant, the other at another, based on how fast the train is moving. And the faster you go, the bigger that difference is. Okay? I didn't do a very good job explaining that, but at any rate, let's go on to this. We can go to the acceleration. Acceleration versus time. It's a little quicker, I think. Okay. We really only have three zones of acceleration. This one is one acceleration, that's an acceleration, and that's an acceleration. Because this is one straight line. And we know that to get from velocity to acceleration, we have to do what? To get from our velocity versus time graph to the acceleration graph, we have to find the slope, right? To go down, we find the slope. So our slope here is change in y over change in x, but that's change in v over change in t, which is a, isn't it? To get acceleration, we find the slope. And our change in v would be vf minus vi, which would be 4 meters per second, minus 12 meters per second, over 3 seconds, which would be minus 8 over 3. Minus 2.7 meters per second squared. This is the slope of the red velocity graph to get acceleration. So our first acceleration is negative minus, and it's minus 2.7. What's my blue zone acceleration? 0. There's no change there. And then the green and the purple, I would have a VF of minus 8, a VI of 4, over 1, 2, 3, 5 seconds, minus 12 meters per second over 5 seconds, 2.4, minus 2.4 meters per second squared. I should have seen that all my accelerations, well, 2 of them are negative, 1, 0. Well, I did them both together because it's one straight line. It's a straight line here. Yes. What? Mm-hmm. What do you mean? Oh, it isn't? Oh, you're right, it isn't. Oh, I'm sorry. I made a mistake. mistake, it's not. You're exactly right, Wendy. The first green one, actually I think it is. So watch. Go down 1, go over 1, right? No, go down 1, go over 2. Go down 1, go over 2. Go down 1. Oh yeah. What did I do differently? Oh, is that what it is? Well, oh, that's what it is. It doesn't. All right. So well, let's do it separately then. So let's do the first one. Okay. I'm sorry. On the first one, we have 0 minus 4 over 2 seconds, right? That's minus 2 meters per second squared. And then in the purple one, we have minus 8 meters per second minus 0 meters per second over 3 seconds. And that's 2.7 again. Yeah, because I screwed up. I thought it was the same slope, but to be the same slope, it would have to be over 2 down 1, over 2 down 1. Okay? So when we graph this, we have to go down to like a negative 3 or so. Minus 1, minus 2, minus 3. This is our A, meters per second squared. The first one was minus 2.7, and that was for 3 seconds, right? And that would be, so that's minus 2.7, see, straight line. And then the next one is 0, and that goes for 3 seconds. And then the next one was minus 2 for 2 seconds. And then minus 2.7 for another 2 seconds. Oh, 3 seconds.